What are quantum numbers and how do they explain electron subshells? This is my presentation on simple words to understand chemistry. We're going to talk about quantum numbers and how they explain the electron subshells as a hemispherical coordinate system. Now, the main concepts in chemistry talk about elements and properties and molecules. And this talk is about the real main introduction to those, which is going to focus strictly on elements. So to understand anything, there are more than one linked concepts. So here you have to understand the atomic model, which is really 3D engineering for how those nucleus and electrons build into shells. Then you also have to understand what is a subshell. Now, to understand this, you have to understand the most important of the properties, and that's the two main forces, the electrostatic and the nucleostatic. So now, specifically, you have to talk about these interaction types. And to understand those shells and subshells, you have to put it into a hemispherical coordinate system. That system is called the quantum numbers, and that equals the logic of each independent subshell. Now, the interesting thing about these subshells, it is really two cylinders that satisfies the work of Nobel Prize winner Bose. Now, the important fields are the Bohr distance radius. That is the place at which the one proton, one electron equilibrium distance. It has a symbol of A sub 0. Now at that point, the radial fields, the electrostatic, which I will use the symbol R, ES, to emphasize that it is radial, thereby isotropic, the same in every direction, no matter which direction you go. It's a shell. There's also the extra 1 over R, which is the strong nuclear force. And by nuclear, I use the word nucleostatic, so you know that it's very similar to the electrostatic, but with different properties. So that symbol will be RNS. Now, the thing is, for the simple hydrogen atom, one proton and one neutron, both of those forces have the same strengths, and that is the Planck constant in the H hat C version. Now, these are the same strength, but they are in opposite directions and equal. Thereby, electrons, as a general rule, want to settle at the Bohr radius if they were just in a 1-to-1 ratio. Thereby, that strength, that Planck constant that we use constantly in both chemistry and in physics, is really Planck at Bohr or Planck at equilibrium. It is the strength at a position within a field. However, the two fields are of different scale. So various adjustments have to occur. Now the two scales are 1 over distance squared for the acceleration of electrostatic force and an extra 1 over r, so 1 over distance cubed for the strong nucleostatic force. So this becomes the chart at the right. The red line is the electrostatic force, okay? It is at 1 over distance squared, and it continues as negative. And so as it gets closer, it gets stronger. and the nucleus would fall into the nucleus, that dilemma. Now, new electrons don't fall into the nucleus, so something else is happening. That is the green line, the nucleostatic, the radial nucleostatic, with that extra 1 over r. Now, normally, a 1 over extra 1 over r decreases faster, exponentially faster. So at any distance, say 10 times the Bohr radius, the strength of nucleostatic is 1 over distance cubed. So 1/1000th of the Planck hc. Well, that's not very much. In fact, it's immaterial. As a result, for hundreds and thousands of years, we've ignored this because our measuring systems, it's immaterial at the distance of where we observe. We observe at a distance only the electrostatic force. However, once it gets inside the Bohr radius, the strange and amazing thing of 1 over extra r is that as it decreases going out, it increases faster going inward. That means the green line is at every point inside Bohr stronger. It becomes a wall of repulsion based upon the number of protons in the nucleus. So you get these orange arrows. That is the net number between that at the Bohr radius, 1 on this graph, is a self-correcting equilibrium. These graphs are positive is physics positive, which is repulsive. Positive meaning the distances will accelerate to increase. Okay? Physics negative, on the other side, is the distances want to decrease. It's a decrease in the acceleration. Now, as you can see, both the red and the green go to infinity, but it's the net number, the black line, that is the basis of electron shells. And the funny thing is that it's 0 at the Bohr radius. But if it becomes less than a Bohr radius, the net number is positive. That means an acceleration positive, pushing it back to the Bohr radius. However, beyond the Bohr radius, this net number is always physics negative. Thereby, you push it back to the Bohr radius. If it goes too far away, it is pulled, distance getting smaller, physics negative. So with that, you can see how the basics of an electron cell is the two of the fundamental forces, electrostatic in red versus nucleostatic, and that generates the Bohr equilibrium. Now, that's not the complete picture. That's a very nice strength versus distance, and that's really in only 3 directions. And not everything is just one-to-one relationships. So let's explain the first relationship. Now, we already know that between an electron, here in yellow, versus a proton in red, there is this net 2 force, this attraction up until it gets to the Bohr radius with this wall of repulsion there. So they would tend to settle at the Bohr radius. However, if you get a second electron, this is how you get a full shell 1. The second electron wants to go to the position at 180 degrees. Electrostatic repulsion operates as a like-kind repel. As a result, those 2 electrons want to be as far away from each other as possible. Yet, they are still net 2 force attracted to the nucleus and the protons by electrostatic. As a result, electrons and polyhemisphere pairs are always at 180 degrees from each other. Now, this is not in the current textbooks, and part of the difference of how I approach chemistry and physics differently. You can see that the polyhemisphere logic works even on dynamic situations. If the electron here is moved off of that position at the Bohr radius at 90 degrees, you will have at number 2 a vector of acceleration towards the nucleus. Yet, those two electrons want to repel each other. So, number 3, the first electron and the second electrons are pushed away. Now, I've translated that vector to the hashed arrow. So the combination of those two becomes pushing that electron along the circle outside the Bohr radius towards that 180-degree position. So just like my first graph about the natural dynamics of settling at the Bohr radius, here you have when multi-particles pairs, there's a natural settling process at 180 degrees. Now, I call this polyhemisphere logic. And that's to remind everybody that the two is not abstract. The true is 3D geometry of how multiple particles actually work together. Now, that's two particles and the simplest things. Now what happens when we get more and more of these particles? Now, first, in here on the right side, I've shown 3 particles in the right rim of a cylinder. The center oval is the nucleus. And on the far side, at 180 degrees, is that polyhemisphere pair with the red arrow making that extra side push out, okay? And stay generally at that. Now, there's also 2 other ones for each of the ones. And in part, this becomes subshell P with 3 electrons in one hemisphere and 3 electrons in a hemispheres offset by 1/2 phase so that each electron has its polyhemisphere pair at 180 degrees. Now, hemispheres then by an electron subshells are 2 hemispheres. They are odd counts, which I'll explain a little later. And that way, all of those electrons are at the same inclination angle, the rim of the end cap of the cylinder, at the same distance. And so that combination gives them the same energy. And so electrons want to fill to that things. Now, look at the parts that make them stay in those things. The red inner arrow is electrostatic attraction, physics negative of electron to the protons in the nucleus. The yellow is the strong nuclear force. I already told you about that radial equilibrium. However, there also is an axial equilibrium. And that's the part I'm adding in this. The weak nuclear force is not radial. It is axial. It goes towards a line, a nucleostatic axis for each nucleus, and in fact, every particle. That is offset by those other 2 electrons, which are spaced evenly, so thereby provide a axial outward electrostatic electron-electron repulsion. So we have 2 radial forces in equilibrium and 2 axial forces in a self-sustaining equilibrium. Now that self-sustaining equilibrium is a little more complex. It is the axial statistical mechanics or quantum because there's more than one unit, but they are individual units. They bounce off each other in unitary quantized behavior. And so it is this axial self-sustaining balance that is the cause of statistical mechanics and quantum theory. In fact, the math of this was described by Bose in his Nobel Prize winning paper in 1924. He talked about polarity, too. Well, that's the Pauli pairs at 180 degrees. And he talked about the cylinder surface math, that somehow electrons never get towards each other's, but they stay in these cylinders. Well, his cylinder surface is my end cap rim. So this gets you finally to quantum numbers. Quantum numbers are the physical hemispherical coordinate systems of 4 quantum numbers describing the 3D engineering, the geometry of those shells. The 2 end cap rings. You also can call them a longitudinal ring or the end cap rim. So the first number is the layer. How many layers have you built? The second number is the inclination angle. Now that starts at the poles because the first 2 go to the poles as in helium. The third number is the latitude. And that's how many, the count of spaced around those longitudinal rings or end cap rims. There's a pair in the fourth other hemisphere. And so by the fourth number becomes which hemisphere. Now the first 3 are counts of number of electrons or number of layers, okay? And so they are quantized, but the last number is not an integer. It is plus 1/2 or minus 1/2. And we use that because for those certain math, we have to use only half of the energy because you're only looking at one hemisphere. Now, a few interesting things as you look at these numbers. The first layer begins at 1, and it's the number of layers you go. Yet the second number, the inclination counts, starts at 0. And that's because it's easier for me in the math to make the angle 0. So thereby my math calculation is counts starts at 0. So 0, 1, 2, 3 for the second number. The third number is latitudes. And how do we count latitudes? Well, integer counts around that spacing. You'll have a meridian, and that will be chosen as your 0, okay? And then you'll have latitudes at plus or minus 1, or plus or minus 1, plus or minus 2 on either side until you fill out that shell. Now that gives you the geometry in the equator view in the bottom right. So the electron subshells at the poles are numbered, quantized, first, 2, and this is the second quantum number, 0, 1, 2, 3. And they're further away from the poles and thereby get bigger. As a result, we now have 3D engineering and a hemispherical coordination system to understand both forces that make electron subshells and all of the quantum theories. Now, there's one more piece you have to understand. Electrons in two hemispheres had those plus or minus. Remember that second subshell is on the opposite side and offset at 100 degrees. The same thing happens then as you add a second layer. At the top right is a famous early picture of electron subshells, and it shows the layers building on them. Everybody was sure this picture showed layers. But what I see interesting in this picture is that the layers tend to be paired, spaced close to each other. That is, a second layer can stay at the same count if it offsets by 180 degrees. So in the bottom, I've tried to show this, at least for the subshell P, 3 in each hemisphere, set for shell 2 and shell 3. So this is a polar view. This is me looking down from the poles. In the center is subshell S. That sits at the pole and likes that. Now the first layer, starting at the bottom as 0, will then have a +1 and a -1 for the 3 electrons. However, instead of having to get a bigger shell, a second layer becomes at the 180-degree position with its plus and minus fitting in the gaps of that inside layer. Now, once you go to a third layer, well, you're already going to be directly above that first layer. So that actually increases the count then and goes to 5. Now, why am I going to 5? Well, that's the fun, amazing math. The periodic table of elements, these shells and subshells build in 3 dimensions, okay? The 2 hemispheres is the first dimension, okay? We know that from the Pauli pairs and from the Bose cylinder math. In the other 2 dimensions, you have pi times radius squared. A circle is the tightest configuration of what you can get of number of units. Now, it is quantized. There are specific counts of electrons, thereby they cannot change. But third, these shells overlap, so you get 2 layers at the same count offset by the half phase. So the periodic table becomes shell 1 is 2 times 1 squared, 2 times 1, which equals 2 max. Shell 2 and shell 3 are 2 times 2 squared, which is 2 times 4 equals 8. Shell 4 and 5 is 2 times 3 squared, 2 times 9 equals 9. And finally, shell 6 and 7 are both 2 times 4 squared, which is 2 times 16 equals 32 max. That describes why we have the periodic table built in those rows of expanding sizes by 2 times the squares. Now, that's not just the end of these fun. It actually becomes that because of that interlapping, you get hemisphere rings of odd counts. It's amazing because to get the squares of units, x plus 1 squared, the extra is 2x plus 1. And it's a unit. Okay, so it's always an odd number. So that means the subshells are also built by squares, but also by odds. So when it's shell 1, you get 2 times 1 equals 2. But the funny thing is that for shell 2 and 3, 1 plus 3, the odds, is 4. And 2 times 4 equals the 8 in subshell 2 and 3. Then 1 plus 3 plus 5 equals 9. But that's the 3 squared from the prior slide. And that times 2 is the 18. And 1 plus 3 plus 5 plus 7 is 16. Another square, 4 squared, becoming 32 electrons. So now we have this model, but that's not flat pancakes. Those electrons are not perfect in one dimension because they space on the inner layers. They are a layer over whatever was inside. So you get the 1 at the pole, then the 3, then the 5, and then the 7, building towards the equator. Now, as you have smaller shells, you only have a 1 in subshell 1, but then you have a 1 and a 3, and an interlaced 1 and a 3, and then a 1, 3, and a 5. So these build layer on layer, but always by a hemispherical coordinate system. Now, the interesting thing is that these distances and layering actually makes them a little offset. You see, the ones at the pole are definitely all lined up. So that means there's a lot of direct repulsion towards them. But those offset ones, as in slide 3, were interlaced. So that means they actually can fit in a little bit tighter. That means that that perfect spherical system is not quite so perfect. So when we finally get to the math of that, you're going to find that the subshell D and the subshell F actually settle inside the subshell S at the pole. They're pushed in. And of course, by their pushing them in, the one that gets pushed out is the subshell P. So the subshell P gets pushed out, meaning it fills with the least amount of the energy because it's the furthest from the nucleus, and also thereby becomes the one that we distribute and bond to last in the off-bow strict filling. So now there's a little more complexity to that, which I'll explain later. But this is the basics of how the quantum numbers describe the 3D geometry and the mathematical model that underlie quantum numbers, as well as everything we know about chemistry.